Thank you. I have a story to tell you, a story in space and time. And this story started 1.3 billion years ago when only single-cell life forms existed here on Earth. And the story is the following. You see here two black holes. One of them is 29 times more massive than our Sun. The other is 36 times more massive. They are doing their final dance together. They are circling each other and speeding up to nearly more than half of the speed of light. And then they are merging. They created a new black hole. This is the first time we could see the birth of a black hole, which is more than a couple times our solar mass. It's 62 times more massive than our Sun. If you listen carefully to these numbers, you may ask, what happened to 3 solar masses? 3 solar masses of energy actually radiated away in gravitational waves. Gravitational waves are ripples in space-time. And this was the first time that we detected them. So we are back to the present, to the detectors which made the observation. It happened on September 14th, 2015, a bit more than a year ago. And actually we just announced it exactly a year ago, February 11th, 2016. That was the first time when the general public could have heard about the existence of these large solar mass black holes and also their mergers and their detection of the gravitational wave imprint from them. The detector up there is in Louisiana. This one is in Hanford, Washington. These are 4-kilometer L-shaped instruments. 4 kilometers, very large size. And there must have been quite a bit of innovation and technology that had to go in there to make this detection. On the next slide, I'm going to tell you how the gravitational wave signal showed up in our detector. You are going to see our signal. It's going to be a waveform which is like an amplitude of the gravitational wave strain versus time. You can look at the time axis. It's going to be just less than a second. It's a short time axis. It's a very quick, fast signal. And also, you're going to see the frequency versus time interpretation of that signal. You will see that the frequency of our waveform increases versus time. So we call this a chirp. But you will not only see the signal, you're also going to hear it. You are going to hear it in the audible band because our detector is sensitive in the audible band. And this is why we say this is the first time we heard a song of the universe. It really is going to be just a chirp, a small chirp, very short one. First, I'm going to show you guys in the real frequency band where we detected. This is at the bottom part of the human audible region. And then I'm going to show you with the increased frequency region, we just shifted it so it's more audible for you. So see and listen. So these are the first detected sounds from the universe. And to detect them, we needed to measure displacement. A displacement which is very tiny. We are zooming into the center of an atom. And this is a proton right now. And the displacement is just a tiny fraction of the size of the proton. What we measured is 4 times 10 to minus 18 meters in displacement. We measured it with an instrument called laser interferometer. I told you guys it's 4 kilometers. To put it into New York perspective, that is Manhattan, and I put an L-shaped interferometer on it. You see that this is a complicated instrument, even in this simple representation. There are suspended and seismically isolated optics inside our instrument. And the basis of the operation is the following. We have a laser there and a beam splitter, which splits the beam in 2 directions. We are going to follow the movement through one of the beam splitters, that's one of our beams, goes to the end mirror 4 kilometers away, turns back, and it will meet up with the beam from the other mirror. They meet up and go together jointly to the photodetector at this end, and they create a signal. And if a gravitational wave comes by, there is a displacement in the system. And we see that here with the signal changing on the photodetector. That is our signal which we detected, and that's what I showed you represented in amplitude versus time in the previous slide. And this is a portion of our detector. LIGO actually has the largest nothing on Earth. It's a huge vacuum chamber. So I wanted to show you, this is just a chair, so you guys can imagine these sizes. Okay, and then we have these tubes going along 4 kilometers in 2 directions. To build this, many people were involved. This concept, laser interferometric gravitational wave detection, started in 1960s. In 1970s, there were very well made out plans. Actually, the elders and the founding fathers of the LIGO scientific collaboration and the LIGO laboratory really spent decades of their life to reach this point. But I don't want to talk about them. You can open the newspapers. You can hear a lot of, different discussions with them online and everywhere. Just search. I want to show you guys some other people who worked with us, some young faces. Okay. This is Maggie. She's a New Yorker, actually. She started to work on LIGO as an undergraduate student at Columbia. She's now a graduate student at MIT. This is another New Yorker, Alexa. It's hard to tell in the bunny suit, but she's really having fun posing in front of the optics. Another pair of young people at the Hanford side, discussing next stages of installation at LIGO. It's hard to tell from the bunny suit who is who on which picture, so I don't know. But I can tell you this is Stefan, and he's putting together timing electronics here in our lab at Columbia, all for LIGO. And these are more young people at the LIGO control room. Okay, they are there. They are even there right now, many of them collecting data. These are the young faces beyond LIGO. It's 1,000 of us, and we're all needed. We needed our founding fathers of the experiment, and we needed these young people as well to reach this point. So I really would like to inspire you guys to start doing science early, at a young age. Discover your interest. At young age,
such
like
a
Alexa
memory
did.
of sitting in the class and being like, that's where I want to work. And it's just amazing that, years later, I'm actually here. I always knew that experimental physics was, 1 step forward, 20 steps back. But coming right out of class where I was, very type A student, crossing things off my list, getting things done, it was a big adjustment for me to learn how to handle being in an experimental environment and not somewhere where the answers are known. So that was really new to me and really exciting. Technically speaking, I also have no electrical engineering background, so that was something new that I kind of dove into here. It's also hands-on, which I like. You know, sometimes after sitting at a computer for so long, I like getting up and actually moving around and adjusting things. I realized I really enjoyed physics. I liked seeing how math was applied to real-world things. And something like this, that's such a challenge, even if it is just fine-tuning something, just overcoming that challenge is really fun to me. If we're able to detect a gravitational wave, and I think we will, it's just going to be huge, just as big as, you know, the Higgs boson was at CERN.
Yes, Higgs boson was at CERN. We are still hoping for that prize, to tell you. At least the collaboration will be very happy if it will happen. So I want to inspire you with 2 more young people, because I show you these well-known physicists here at their fairly young age. Einstein, in 1905, when he really made one of his greatest works, for example, E = mc squared, he was only 26 years old. So those of you who are in high school, get started right now, okay? Marie Curie, she was also very young, late 20s, early 30s, when she worked on the radioactivity with her husband and Becquerel. And she was only 37 when she got her first Nobel Prize. Amazing. She was young, right? She was young. You are young. Keep working, because we have a lot of work for you in science. I'm going to give you some examples what you have and you can work on in gravitational wave science. This is our current knowledge of black holes, which are in the couple solar masses to, 100 or 70, in this case, solar masses range. These pairs were discovered by LIGO. We've probably seen a third pair. This is what we know right now. We may have more in the data, and whenever we hear, we are filling up this table. But in a couple years, we are going to detect them, maybe even daily. We are really going to have a good understanding on the parameters of these black holes. We'll understand the statistics, how far they are formed. We'll learn a lot about them, and we will fill up this table. It is really a fun work, and the astrophysics which is coming out of it is even more amazing. There could be lots of unknowns which we just never expected to see. This is what we have seen in September. This banana here, and that hump, it tells us where our signal may have come from. This is the full sky, so you guys can tell we don't really know where our signal came from. We can tell how far it was, but we can't really tell the direction. But a lot of new things are coming online. In probably a month, Virgo will start operate. So with 3 detectors, we are going to have already better position reconstruction on our signal. And then we are going to have a detector in Japan in a couple years underground. We will be building LIGO India, and we need young people. So if you get started right now, in a couple years, you may go and help us building LIGO India. And then there is an amazing small detector existing in Germany, which is our test bench for next generation detectors, because we, in the gravitational wave detection field, are dreaming big. We are dreaming big of a large-scale instrument, tens of kilometers size, and seeing very, very far into the early universe. We need a lot of technology improvements to get there, and our test bench is there, one of our test benches. Okay. There are scientific questions additionally. It may come early. I really hope this issue will be not necessarily solved, but will be observed. These are 2 neutron stars. We really would love to see them to merge and collide, giving birth to a black hole. But not just black hole, also electromagnetic radiation in form of optical light, gamma ray bursts, X-rays, and we would love to detect them. We need astronomers, who some of them are working right now on satellite data or regular optical telescopes to help us to follow up. Maybe we have another messenger together with the gravitational wave from the same cosmic event. We may see them with neutrinos. This is Ice Cube at the South Pole, which is looking for cosmic neutrinos. And if we have a joint signal detection, that will be the dawn of gravitational wave multi-messenger astronomy. We can't wait for that field to start. Okay? And if you would love to work even in further distances and also with larger black holes, we can make an instrument which is working in a different frequency regime and is sensitive to black holes which are much more massive, like supermassive black holes. Okay? We can go to space for that. This is a project planned by ESA, the European Space Agency, and it's likely that it will happen in 10 years, 20 years or so. You are young right now. It's going to be your generation. So please go ahead. Dream big. Go to talks. Go to talks because you don't know what else you will find there. You will find certain inspiration at a scientific talk, but I can tell you a short story from my life. At age 16, I met my husband at the local college at a scientific talk. We have been sharing many excitement in life together, excitement and discovery, and also for children. So you never know what science and going to talks like this will bring to you. Keep dreaming big. Ask difficult questions from yourself and everybody else, and work persistently, like the elders of the LIGO experiment did. The science, the future in science is yours. Thank you.